get started in terms of preparation for calculus. And let's review the function and their graphs. So in this particular PowerPoint presentation, we're going to use function notation to represent and evaluate a function, find the domain, the range of the function, sketch the graph of function, and also learn how to identify different types of transformations of functions, classify functions, and recognize combinations of functions. And first of all, let's take a look at the function and then function notations. So function is a one-to-one relationship. So it's a key feature of the function. It's one-to-one relationship between the variable x and variable y. And then we call variable x a dependent variable, independent variable, and variable y is called a dependent variable. And then the key thing about this is the one x value produced or yields only one, and then only one y values. So that will construct the function. And function can be specified in a variety of ways. However, we will concentrate primarily on functions that are given by equations involving the dependent and independent variables. For instance, the equation x squared plus 2y equals 1. So this is the equation. Here, y is a dependent variable, and the x is independent variable. So if you want to rewrite this, x squared plus 2y equals 1, express that in terms of y. We subtract x squared from both sides of the equation. So 2y equals to negative x squared plus 1. After that, we divide both sides of the equation by 2. We get a cancel 2, y equals to negative half of x squared plus half. Another way of writing this is factorial negative half. Then we have x squared plus 1. So y value equals that. So evaluate the function y value that corresponds with given x values. I already did a transformation, and if you factor half, then you're gonna end up with y equals half times 1 minus x squared. And this is what they call equation in expressive form. And the function notation is just basically rewrite y as f of x. Right? You have to put in the function notation. So anytime if you need a function notation, you're going to do f of x equals to, let's say, ax squared plus bx plus c. So this is the function notation for quadratic equations. Now let's take a look at an example. We have a function f of x equals to x squared plus 7. So we want to evaluate each expressions. First of all, we get f of 3a. F of 3a, basically you just replace x in your original equation with 3a. In this case, x becomes 3a. So we get a 3a squared plus 7. In that case, we have a 3 squared becomes 9, a squared plus 7. So that's going to be the answer. This is the a part. B part, we have f of b minus 1. So f of b minus 1, in this case, you're going to replace x here with b minus 1. So we have b minus 1 squared plus 7. So we have b squared minus 2b plus 1 plus 7. When you expand the perfect square, you're going to end up with that. And we combine actions, we get b squared minus 2b plus 1 plus 7 give us plus 8. So the answer is b squared plus 2b plus 8. The last one is finding f of x plus delta x minus f of x over delta of x. So for f of x plus delta x, we replace x here with x plus delta x squared plus 7 minus f of x, which is x squared plus 7 over delta of x. And when you expand this, we're going to get x squared plus 2x times delta x plus delta x squared plus 7. When you expand the second parenthesis, put back invisible 1, distribute x squared minus 7. In that case, we cancel x squared, we cancel 7. So the final result is 2x delta x plus delta x squared over delta x. Then we cancel delta x, we're going to end up with 2x plus delta x. Okay, that's a detailed solution. On the second page, you confirm our answers. Okay, we can take a look at it. Actually, let's take a look at the domain and the range of a function. So the domain basically all possible x values. Range are all possible y values. Okay, so that's basically the essence of domain range. So the domain is a set of all real numbers for which equation is defined, meaning all possible x values. So for example, let's say, let's take a look at this function g of x equals to 1 over x squared minus 4. Since it's a rational function, right, so the domain cannot be 0, right, so we're going to say x squared minus 4 cannot be equal to 0, right, so adding 4 from both sides. X squared cannot be equals to 4. In that case, x cannot be equals to plus minus 2. So the domain will be all real numbers, or will be this. All real numbers except x equals plus minus 2. Plus minus 2. Okay, so let's just look at the domain and range. This function, radical functions, f of x equals radical x minus 1. So in this case, for radical functions, the domain must be whatever underneath the radical. X minus 1 must be greater equal 0. Then you add 1 from both sides, x must be greater equal to 1. Then using the function notation, that will be interval notation, right? It will be from 1 to positive infinities, right? Including 1, so that's going to be the domain. same thing as 1 range. After you graph the function, you see something like this. As you can see, the graph going upwards and going upwards forever. That means everything on the y-axis works. So starting with 0, right? 0 to positive infinity, that's going to be the range. So the range is 0 to positive infinity, as indicated in our graph. And as you can see, the domain of tangent function, which is f of x equals tangent of x. All of these dashed lines are what we call asymptotes, right? This is what they call asymptotes. You see this in your pre-calculus class. So asymptotes are some curve or line which the graph gets infinitely close but never touches it. So all these asymptotes becomes our restriction on the domain. In this case, x cannot be equal to pi over 2 plus n pi. So meaning all real numbers except pi over 2 plus n pi, right? So this is the domain. Domain is all real numbers except x equals to pi over 2 plus n pi. So that's gonna be our domain. Okay. So a function from x to y, x is independent variable, y is independent variable, is 1 to 1 if to each y value in the range that corresponds exactly one x value in the domain. One value, each value corresponds to exactly one x values in the domain. So that's going to be the function. Next, let's take a look at the graph of function. The graph of function y consists of all points x, y, same thing as x, comma, f of x. Y is the same thing as f of x. But x is the domain of the function. And then the x value is the direct distance between the point and the y-axis, right? Like this. And since this is equal to that, so the x value comes from that. And the y value is the direct distance between the point and then the x-axis, which is this length. And this is the same thing as that. That's why this is our y value, f of x. Okay. So we have a very unique test called vertical line test. And vertical line test to determine whether or not a relationship is a function. Determine the function. So in this case, if vertical line only intercept every single part of the graph with only one intercept, that means it's a function. Right? If we have more than one intercept, then it's not a function. Let's take a look at this demo about the function. So you go vertical line on the first graph. Right, you can see you're gonna have two intercepts, right? Just like the dashed line shows. So vertical line, you get two intercepts. In that case, two intercepts indicates it's not a function. And for the second graph, if you can see, if you draw any vertical line, right, you're gonna only have one intercept. Vertical line at any part of the graph, you only have one intercept. One intercept indicates it's a function. For this piecewise function, you draw the vertical line and one intercept. Right, some parts of the you have no intercept. So 0 or 1 intercept also renders function. Right? So the maximum amount of intercept you can have in order to be qualified as a function must be 1 or less. As you can see, this is the following is 8 basic functions. Going from the linear equation, x equals x, so the linear equation passing through the origin is the origin. The slope is 1. The second is squaring function, or what they call is quadratic equation. This one also has passing through the origin. It's symmetric by the y-axis. The third one is a cubic function. From left to right, it's increasing all the way. Right? And the fourth one is a square root function with the square root of x passing through the origin, and it's going upward. Fifth one is an absolute function, absolute value function. And it's symmetric by the y-axis. The sixth one is a rational function. In this case, both x-axis and y-axis are asymptotes for this rational function. The next one is a sine function. One period for sine function is from 0. One period is 2 pi. From 0 to 2 pi, that's 1 period. And the amplitude. Amplitude is 1. And the last one is cosine function. So period is also 2 pi, 0, 2 pi. Particular 1 period. So period 2 pi. Amplitude is also 1. Okay, so that's the cosine function. And it appears in the cycle, right, for both sine and cosine function. And next thing, let's take a look at the transformational functions. Some typical transformation is shifting upward, vertical shift upward, like this one going from y equal to x squared to y equals x squared plus 2. You basically shift up 2 units, 1, 2, right? And going up 2 units. This one is horizontal, second graph is horizontal shift left 2 units. Start from. So start here, 1, 2, and here. Third graph shows a fraction about x-axis. Fraction about x-axis. The very last one is a series of transformations. Start with shift 3 units to the left. Right. 3 units to the left and shift 3 units to the left. First transformation. Second step is it has a refraction about x-axis refraction. About x-axis. And last step is shift upward, shifting up in units. Shift up. Shift 1 unit. Once you perform all these 3 transformations, you reach the new graph, which is in black. So this is a typical transformation on a graph for the function x squared or f of x squared. So 3 basic transformations. First one is vertical shifts. Second one is horizontal shifts. Third one is fraction. Function notation lends itself well to describing transformation of graphs in a plane. For example, let's say for f of x equals x squared, considered to be the original function. So the transformation could be represented by the following equation. So y equals f of x plus 2, basically vertical shift up 2 units. Second one equals f of x plus 2. You will horizontal shift and graph to the left 2 units. Third one, have y equals negative f of x. It's a refraction about the x-axis. The last one equals negative f of x plus 3 parentheses plus 1. So you shift left refract about x-axis and shift up to 1 unit. So this is a summary of typical transformation. For example, if the original graph is y equals f of x, so horizontal shift c units to the right, you subtract c from the x. Right, you come out with y equals f of x minus c. And the second transformation is horizontal shift c units to the left. You add in c to the x. Right? Third type of transformation is vertical shift c units downward. So you subtract the function f of x by c. And the fourth one is vertical shift c units upward. So you're adding f of x by c. And the fifth one is a refraction about the x-axis. Then the function becomes y equals to negative f of x. x1 fraction of y-axis, then you replace x with negative x in the original function. So I have y equals 12 negative x. The last one will be a reflection about the origin. So place x with negative x and replace f of negative x with negative f of negative x. So double negative sign in front of x, in front of the f. Okay. So those are the 7 basic type of transformation. Should definitely go over the PowerPoint presentation itself, also the audio recording more than once if you need to, if it requires you to comprehend this stuff. Because transformation is not a very easy topic. Okay, so next typical classification combination of functions. Typical term is what they call composite function. By the end of the 18th century, mathematicians and scientists have concluded that many real-world phenomena could be represented by mathematical models taken from a collection of functions called elementary functions. So an elementary function has 3 typical categories. 3 categories. First one is algebraic functions, like polynomial functions, functions, rational functions. Second group is trigonometry functions, including sine, cosine, tangent, cotangent, cosecant, and secant. The third category is called exponential and logarithmic functions. Right? The 3 typical elementary functions. So the most common type of algebraic function is the polynomial functions, with f of x equals a subscript m x to the nth plus a subscript n minus 1 x to the n minus 1. You have infinite many terms and it ends with a constant a0. So n is a non-negative integers. Remember, a subscript I are coefficients, where a subscript m is the leading coefficient, a0 is a constant term of the polynomial functions. So if an not equal to 0, then n is the degree of the polynomial functions. So for the polynomial functions for 0 degree, so we get f of x equals to a, so it's a constant function. First degree renders f of x equals ax plus b, that's a linear function. Second degree renders f of x equals ax squared plus bx plus c, so this is a quadratic function. Third degree, f of x equals ax cubed plus bx squared plus cx plus d. So that's a typical cubic function. Although the graph of non-constant polynomial functions can have several terms, eventually the graph will rise or fall without bound as x moves to the right or left. The second one is rational functions. Okay. So we have f of x equals to px or qx. P1, p, and qx are both polynomials. I can give you a quick example. A typical rational function, x squared over. Both of them are polynomial functions. numerator and denominators. So polynomial functions, rational functions are what they call it algebraic functions. So an algebraic function of x is one that could be expressed as a finite number of sums, difference, multiples, quotients, and radicals involving x value. For example, f of x equals radical square root of x plus 1 is algebraic. Function that are not algebraic is called transcendental. For instance, the trigonometric functions are transcendentals. Trig functions. Two functions can be combined in various ways to create new functions. For example, given that f of x equals 2x minus 3, g of x equals x squared plus 1. So f plus g parentheses x is f of x plus g of x. So you add in these two functions. That's what they call stuff. Difference is parentheses f minus g x. And basically it's what we perform is f of x minus g of x. And subtract two functions. And the third one is the product. So f times g parentheses f of x, meaning f of x times g of x. F slash g parentheses x equals f of x over g of x is 2x minus 3 over x squared plus 1. So this process is called composition process. And the resulting function from the composition process is called a composite function. So composition function comes from composition process. So this is a typical definition of a composition function from textbook. So that f and g be functions. The function given by f composite of g parentheses of x is called a composite of f with the g. Right? The domain of f composite of g is the set of all x values in the domain of g such that g of x is in the domain of f. The composite of f of g may not be equal to the composite of, now this is very important, may not be equal to the composite of g with f. Depends on the function. Here, let's take a look at the example. Let's say f of x equals 2x minus 3, and g of x equals the cosine of x. And let's find each composite function. So f of g, f composite of g. So here is basically f of g of x. So for the original f of x, replace x with g of x, which is cosine x. So here we write 2 times x now becomes cosine x. 2 times cosine x minus 3. Okay. So b pi is g composite of f. So g of f x. So that becomes g of f of x. So this is basically becomes replace x here with 2x plus 3. So we have cosine of 2x minus 3. So this is detailed solution from your. As you can see, f of g of x and g of f of x is not the same. Go back to really quick. No, the result does not come out the same. F of g in this case definitely is not equals g composite of f. Okay, so it's something you have to pay attention. And classification and combination of functions as x-intercept the graph is defined to be a point A, 0, at which the graph crosses the x-axis. The graph represents a function of f. Number A is a zero of f. In other words, the zeros of function f of x are solutions to the equation f of x equals 0. So basically, in order to find the x-intercept, you set y equals 0 and solve for x. That's what this is about. And next thing, let's take a look at even and odd function notation, right? The terminology of functions. So function is even if its graph is symmetric with respect to y-axis. If it is odd, its graph is symmetric with respect to the origin. So for even function, f of x is equal to negative f of x equal to negative f of negative x. This is our function. F of x is equals to negative f of x. So it's not just another way of writing even and odd function. It's pretty consistent with the test for even and odd functions given in the PowerPoint. Now let's take a look at these two functions, determine whether or not they are even or odd functions, or neither, right? It could be neither functions. So first of all, f of x equals to a x cubed minus x. Now we just gotta figure out what is f of negative x. Okay, so f of negative x, replace all the x with negative x. Then when you expand it, you end up with negative x cubed. Minus become plus x. As you can see, compare the result if you factor out negative sign. And we have x cubed minus x. And these terms are exactly f of x, right? So in this case, we have f of negative x equals to negative f of x. And this is exactly the definition of the odd function. B, we have g of x equals to x. 1 plus cosine x. Now we replace x with negative x. Let's find what is g of negative x. So it's going to be 1 plus cosine And we know that cosine x is even function, so in this case, plus cosine x. And this one plus cosine x is exactly g of x. Now we have a relationship with g of negative x equals g of x. And this is exactly the definition of the even function. So the answer is even function.